you should keep in mind that this is an introductory course in differential equations, so a lot of what we're doing is just basically solving lots of similar problems, just as you did in calculus, and we're just basically honing our calculus skills and understanding how differentiation, integration is used to both model real situations and actually then find solutions to those problems. In Chapter 7, the book goes through a handful of very basic applications: exponential growth and decay problems, temperature problems, falling body problems, dilution problems, electrical circuit problems, and something about what's called orthogonal trajectories. We're going to focus on just the three of those for this course: just growth and decay, temperature, and the falling body problems. These are the ones I'm confident that most of you have at least had some experience with in calculus in some form or another. At least understand exponential growth and decay, temperature problems, and falling body problems. The electrical circuit problems and the orthogonal trajectory problems, those are a little bit more advanced, and you may not have seen anything related to that. So we'll just kind of study those on your own if necessary, but the point is these are all just basically applications of very basic first-order differential equations. Most of them are linear, in fact, linear equations. So I want to use the temperature problem as the model here, but you could do this for a lot of the other problems, both the exponential growth and decay problems and the falling body problems, in a similar manner. We saw that the model for the temperature problem is given by this linear differential equation, where T sub m is a given constant, the room temperature that the object is in. Capital T is the unknown function, temperature function of the object that we're looking to find. It depends on time in this case, or lowercase t. And again, in differential equations, we often suppress writing the parentheses of little t or of little x, depending on our independent variable, just to focus on the fact that we're actually solving a whole bunch of equations at once. We're trying to find a function, basically all the outputs of a function simultaneously. So our unknown is really the function. And again, k in this model is just comes up from our interpretation of the thermodynamics, the laws of thermodynamics. So this is related to how fast the object will actually cool. So different materials will cool or heat up faster when placed in a room of a certain temperature. So this k is dependent on the actual object. So again, as a linear equation, we know how to solve those. It's a very specific process. And we saw there that we really don't have to resolve each one independently. We just have to identify a couple things that we have to anti-differentiate and then plug them into a formula to get a general solution. So this temperature problem is similar. We solve the linear equation to get the general solution. Again, T sub m is a known number that we will know. And now the constants c and k are the only unknowns that we have. All right, k is related to the rate at which the object is heating or cooling, and the constant c is really just the initial temperature of the object. Well, it's related to the initial temperature of the object. So just kind of what do we typically have? We're typically given two pieces of information, and that's because we have two constants in this term, this exponential term, that are unknown. So generally speaking, if you have two parameters or constants in your formula that you want to determine, you're going to need two pieces of information to help determine those. So the initial temperature is given to us typically as some number t sub 0, but the interpretation is that that is the value we get when we plug time equals 0 into our solution function. And we're also given some future temperature oftentimes, so some temperature t sub 1 at some future time, lowercase t sub 1. So those are the pieces of information that we use to determine this c and this k that we have in the exponential term. So the question is, can't we just solve this problem one time without plugging in any numbers and get a formula for the solution of such a problem? And then we just have to plug in all the given information. And that given information is going to be these four things. So the room temperature, the given initial temperature, the given future temperature at some time, future time, lowercase t sub 1. So we want to basically write our solution in terms of these parameters, and then once we see a problem like this, all we have to do is plug in those values. So here's the general kind of problem that we're solving here. Suppose an object with initial temperature t sub 0 is placed in a room, temperature t sub m, and at time lowercase t sub 1, which is some future time, so it's generally positive, we know the temperature is some number capital T sub 1. So what is the temperature function? Right, so again, we already know what the general solution is. The general solution has this form. The initial condition tells us to plug in 0 for lowercase t, so that gives us the equation that t sub 0 is t sub m plus our constant c, so therefore we know what constant c is. Constant c is just t sub 0 minus t sub m. Now using that, we use the second piece of given information. We know that the temperature at time lowercase t sub 1 is equal to capital T sub 1. So taking this equation, the only unknown in this equation now is k. So let's solve, not for k, but let's go ahead and solve for, we're going to solve for negative kt, because that's what we see in the exponent. And this will allow us to simplify things by using properties of logarithms and exponentials. So what is negative kt? Well, I just have to take our equation here. I have to subtract a t sub m, and then I have to divide both sides by these t sub 0 minus t sub m, and then I have to take a logarithm of that. And then I have to divide by little t sub 1. So solving for negative kt, we just get negative kt is this quantity here, this t over t sub 1, so t is a variable, t sub 1 is some number we know, times the logarithm of this number that we know. Now just using properties of logarithms, this t over t sub 1 can be brought up as a power on the input of the logarithm. So that's how I write it here on the right side. So negative kt is just this logarithm. So e to the negative kt is just the stuff inside of the logarithm. And that gives us our general solution that we see here. The room temperature plus the difference between the initial and room temperature times some number that we know to a power t over t sub 1, where t sub 1 is the time that we were given the future temperature, capital T sub 1. So any problem like this, you're given the numbers t sub 0, t sub m, t sub 1. You can just plug them into this formula and you'll have your solution without having to redo all the calculus. Well, the point is you can do this for all the other models as well. The only difference is sometimes the given information is given to you in a different way. So, for example, it may not be given to you that t sub 1 may not be given to you. Instead of saying, well, the temperature after 1 minute is 50 degrees, they could tell you that the temperature decreases by half after 5 hours. Well, you can interpret that and translate that into a information that gives you this capital T sub 1 and lowercase t sub 1 so that you can use this formula.